Alright, now let's talk about the alternative classical measures of dispersion. I'm thinking about mean absolute deviation, and after that we will talk about the coefficient of mean deviation. First goes mean absolute deviation. Mean absolute deviation is an alternative classical measure of dispersion. We denote the mean absolute deviation using the symbol of d with x subscript, which indicates as the symbol of analyzed variable. As you can see, instead of squares of deviations, we alternatively use the modules of deviations. But one thing remains the same. Here we subtract arithmetic mean from the values of the variable. Our measure indicates the average module of deviation of the variable values from the mean. As you can see, in the denominator we have the sum from I equal 1 up to n, in which we have the modules of deviations of the variable values from the mean, and this sum is divided by the population size in the individual series, if we of course know all the values of analyzed variable. Chosen selected properties of our measure. They are actually the same as the features of the standard deviation. The unit of mean absolute deviation is the same as the unit of the variable. Mean absolute deviation is computable for all measurable variables. Mean absolute deviation takes only non-negative values. The larger mean absolute deviation, the larger dispersion, and so on. Everything is the same as earlier, but here we have an additional information. Mean absolute deviation is not higher than standard deviation. So it is caused by the fact that we operate by modules instead of squares. Because we are trying to determine the distances between the variable values and their mean distances. Here we use modules. Earlier we used squares, but the main idea remains the same. I want to compute the average distance, the average deviation between the variables values and the arithmetic mean. This slide presents the first task, which is connected with the topic mean absolute deviation, task 4. In 2018, from April to September, the sum of monthly precipitations in Krakow was equal to 401.9 millimeters. So here we are talking about the variable, which is called monthly precipitations. We can name this variable using the symbol of, for example, yi. This is the sum of monthly precipitations, and we know that the sum of monthly precipitations in that time period from April to September, the sum of monthly precipitations from April to September, we have 1, 2, 3, 4, 5, 6 observations. So this will be the sum from I equal 1 up to 6 observations of yi, is equal to 401.9 millimeters. Okay, I have another information about my variable y. Mean absolute deviation of the values of variable y of discussed precipitations was equal to 27.1 millimeters. And that's all. Yes, that's all information about the precipitations. The rest of the task content tells us something about the average temperature, monthly average temperature. It's another variable. Let's name it using the symbol of xi. Knowing monthly average temperature in Celsius degrees in these months, see table below. So here we have detailed information about other variable, values. Please answer the question in respect of which variable Krakow is more differentiated. So let's summarize the problem mentioned in the task content. We have one object, Krakow, yes, and we have six informations about we have six observations of the temperature and six observations of the precipitations in Krakow. Yeah, so we can describe our town by two variables, variable y and variable 2. In our case, we have variable x and variable y. X is monthly average temperature, y is the sum of monthly precipitations. And of course, we know that we have measured these variables in the time period 6 months. Yeah. So we have the time series, we have Krakow, yes, and Krakow can be described by two variables. And now we want to answer the question in respect of which variable Krakow is more differentiated. Yeah? In respect of which variable Krakow is more differentiated. In respect of monthly average temperature or in respect of the sum of monthly precipitations. Yeah? Alright. We have two variables, but the information about variable y is limited, yes, because the only things we know is the sum of the monthly precipitations in next 6 months, and here we have the final result, actually, mean absolute deviation of the sum of monthly precipitations. Yeah, and here we have something else. Here we have detailed information about the temperature in a particular month. So on the basis on this information, in order to make a comparison, yes, make a comparison of differentiations, we should use the same measures to describe the differentiation of the average temperature. Yeah, here the task content indicates us that we should use mean absolute deviation and coefficient of deviation in order to compare the differentiation between the variables. Yeah, so we should compute also mean absolute deviation, the same measure, mean absolute deviation of monthly average temperature. Yeah. it's not a good habit to compute here, for example, standard deviation, yeah, because standard deviation has different construction, yeah, from mean absolute deviation. So it's not a good idea to compare with different measures. We need the same measure, dx, yeah. So let's start. The first step, yes, is to show the formula for mean absolute deviation of monthly average temperature. This will be the sum from I equal 1 up to 6, the sum of modules in which we have xi minus x mean, yeah, divided by n, the number of observations here, because we are talking about the time series, yeah, with time series with monthly frequency. Let's build the first column. In the first column, I need the difference between xi and x mean, and simultaneously I can compute in my head the module of this kind of difference. Yes, this kind of subtraction. Okay, but I don't have any information about the mean monthly average temperature in that period. So first of all, I should compute mean x. Mean x is the sum from I equal 1 up to 6 of xi divided by n. Yeah. So I should sum up that column 13.6 plus 17 plus 18.9 plus 20.2 plus 20.8 plus 16, and the result is 106.5. And then arithmetic mean of the monthly average temperature in period from April to September is 106.5 divided by 6 observations, and the average temperature in this period was 17.75 Celsius degrees. Okay, it's my reference point. Now I'm trying to investigate the deviations of the variable values from their mean, yeah, and immediately I can compute in my head module of mentioned deviations. So in the first step we have what? We construct the column xi minus x mean, the module of the difference between xi and x mean. In the first step I have what? 13.6 minus mean 17.75, and the module of the module of this kind of difference is 13.6 minus mean, it's 4.15 plus 4.15 because this is the module, yeah, this is the module of the difference. After that we have what? Module 17 minus 17.75, and this is of course 0.75. So in that column, I'm trying to catch the distance, yes, between the variable values and the arithmetic mean for each value of considered variable. And the next values are all right, 1.15, 2.45, 3.05 and 175. Yeah. All right. So I have computed all modules. Yes. So now I am able to compute the sum of all modules. The sum of the modules are 13.3. And now finally I can compute mean absolute deviations of monthly average temperature in this time period. dx is equal to, as you can see, the sum of the modules. The sum of the modules is 13.3 divided by 6. 13.3 divided by 6 is approximately 2.217 Celsius degrees. Okay. All right. So we know the average level of the temperature in time period April to September. We know also the average deviation. Yes, the average deviation of the temperature values, monthly temperature values from the mean temperature from April to September. Okay, and the interpretation of this amount is the same. We're using the same example of sentence like in standard deviation. So we can say that average monthly temperature in Krakow during the time period from April to September 2018 deviated from the mean on average by approximately 2.2 Celsius degrees. Yeah, average monthly temperature in Krakow during the time period from April to September 2018 deviated from the mean on average by approximately 2.2 Celsius degrees. Yeah, here we have mean temperature during this period, and we know that the average deviation of monthly average temperature is plus minus 2.2 Celsius degrees. Okay. I have received this kind of information set. I have the information about mean absolute deviation of average monthly temperature and monthly precipitations in the time period from April to September, and I have computed mean monthly average temperature in the time period from April to September. Yeah, I don't have any information about mean monthly precipitations, but I have the necessary information that will allow me to calculate the average. Yeah, this is the sum of monthly precipitations from April to September, which is equal to 401.9. As you remember, the average of y variable values, it's the sum from I equal 1 up to n of yi divided by n. Yeah? Here we have the sum of yi values, 401.9 divided by 6. 401.9 divided by 6 is approximately 66.983 millimeters. Fantastic. I have all the information that I need to answer the question in respect of which variable, monthly average temperature or monthly precipitations, the Krakow was more differentiated. Or in other words, which of the variables in Krakow was characterized by greater variability. Yeah, variability. So deviations expressed as a percent of the average, the typical level of considered phenomenon. Okay, but I have noticed that I have a little problem here, because we have two different variables expressed in two different units. So how to compare? How do I compare Celsius degrees with millimeters? I have to divide the units, remove the units from my analysis. So the next step is to introduce you to another relative measure of dispersion, yeah, which is called, wait a second please, technical problems, alright, which is called coefficient of mean deviation, CMD. Coefficient of mean deviation is equal to following relation. This is a ratio, this is a coefficient, ratio between mean absolute deviation and arithmetic mean. Yeah, so the reference point is the same, arithmetic mean. Here we use alternatively mean absolute deviation instead of standard deviation when we have talked about the coefficient of variation. So coefficient of mean absolute deviation can be denoted by the symbol of V with D. D indicates the measure that have been used in the construction of this measure. And the properties of CMD are analogous to the properties of coefficient of variation. So now we are able to compute both coefficient of mean deviation for the temperature and coefficient of deviation for the monthly precipitations. Here Vdx is equal to dx divided by x mean. In our example, we will divide 2.217 by Celsius degrees, of course, by 17.75 Celsius degrees. Yeah, we can delete Celsius degrees. Now we have no units. And the final result, the relative differentiation is equal to 2.217 divided by 17.75, 0.125, 12.5%. Yeah? Analogous coefficient for y variable monthly precipitations, it's dy divided by y mean. In our example, we divide 27.1 millimeters by 66.983 millimeters. Yeah, we remove the units from our fraction and we receive 66.983. Oh, we receive 0.405. Okay, and the main conclusion is following. Vdy is remarkably higher than Vdx. What does it mean? It means that the sum of monthly precipitations is characterized by higher variability in Krakow than average monthly temperature. So Krakow is more differentiated in respect of monthly precipitations. Yeah, because this variable is characterized by higher variability. In case of average monthly temperature, we are talking about the low variability of variables values. In case of monthly precipitations, we are talking about high, moderate, high variability of monthly precipitations values. Yeah, so as you can see, Krakow is more differentiated in respect of monthly precipitations. Alright, now we will try to calculate mean absolute deviation in the interval series. Here we have task 5. The table below shows the information about the size distribution of men's and women's shoes in Paris points. You know, this is our European scale of shoes dimension, manufactured by a certain fake company. And here we have 4 classes of shoe size. Shoe size is our variable, and shoe size characterizes 2 populations. Here we have population 1, here we have population 2. Population 1 are actually women's shoes. population 2 are men's shoes. Yeah? Here we have the information about the cumulative distribution of women's shoe size, yeah, as a percentage of the total number of women's shoes. Here we have the cumulative distribution of men's shoe size expressed in an absolute terms. Yes, because here we see the number of shoes that are characterized by the shoe size not higher than the upper bound of a particular class. So we have one variable, for example xi, and two different populations. And our main goal is to answer the question which population, men's or women's shoes, are more differentiated in respect of shoe size. In other words, we are trying to answer the question which population, which shoes, men's or women's, are more similar or more different from each other. Yeah, in point of view of shoe size. All right. Here we have the first command. Please decumulate the cumulative categories. Yeah, because we here it's necessary to have to operate by non-cumulative categories. Fi with W subscript, yeah, and Ni with M subscript. Yeah, two different population. Women's, men's shoes. Okay, so now I'm trying to decumulate the cumulative categories. First, relative frequency is equal to first cumulative relative frequency, 0.426. Yeah? The next frequency is a difference between the second cumulative relative frequency and the first cumulative relative frequency, 0.821 minus 0.426. And the final result is 0.395. And the next relative frequency will be 0.949 minus 0.821. 0.128. Yeah? And the last one is the difference between the last and the previous cumulative relative frequency. It's 0.051. Yeah? Here we see the decreasing trend in the relative frequencies. So it means that the most of women's shoes are characterized by low shoe size. Yeah, small, low shoe size. Okay, and here we have the information about men's shoes. So first, Ni category N1 is equal to first cumulative category 55. And now here we have the difference between 125 and 55. So this is 45 plus 25, so it is 70. And now we have the difference between 397 and 125. It's of course 272. And the last one is the difference between the population size of men's shoes and the previous cumulative frequency. So this is 203. Yeah. So I have decumulated all cumulative categories. So now I am able to compute the mean value, yeah? Mean shoe size, average shoe size of men's shoes and average shoe size of women's shoes, yeah? In the first case, women's shoes, I know that X mean for women's shoes is equal to the sum from I equal 1 up to 4, because we are dealing with 4 classes. The middle of the classes multiplied by Fi with a W subscript. If I want to compute the average shoe size for men's shoes, I need to compute first the sum from I equal 1 up to 4 of the middle of the classes multiplied by the frequencies, and divide the sum by the population size here, actually with M subscript. We don't know the population size of women's shoes, but it's not a problem here. Alright, so I should start with the middle of the classes. Here we have the middle of the first class is the value exactly between 36 and 38, so it's 37. Here we have 40, here we have 43 and 46. Yeah? So here I'm going to multiply the middle of the classes and the relative frequencies connected with the women's data in order to compute average shoe size of women's shoes. So first I multiplied 37 by the first relative frequency connected with the women data, 0.426. 37 multiplied by times by 0.426, and the result is 15.762. The next value is the product of 40 and 0.395, 15.8. And now I multiply 43 by 0.128, 5.504. And in the last row I have the product of 46 by 0.051, 2.346. Yeah? Alright. So I have to delete these formulas because I need another column, the summary column. Yeah? Maybe we can start here. the summary column. Okay, here we have 600. Here we have we should have the result consistent with the theory, and here we don't have to sum that column. I need, as I said before, the sum of that column in which I have the middle of the classes and multiplied by the relative frequencies. Let's start to add the values in that column. 5.504 plus 15.8 plus 15.762, and the sum of this column is 39.412. Yeah, so this is average shoe size of women's shoes. And now it's time for to compute the average men's shoe size. For this purpose, I'm going to multiply the middle of the classes and the frequencies, yeah, connected with the men's data. All right, in the first row, I multiply 37 by 55. 37 by 55. The result is 2035. In the next row, we have 2,800, of course. 33 by 272 is 11,696, and in the last column I have 36 by 203, it's 9,338. Yeah, of course, similar to the previous case, I have to compute the sum of that column and divide the sum by the population size. Yeah? So now I'm adding the values in that column. And the sum of that column is equal exactly to 25,869. So this is my partial result. 25,869 divided by the population size. The population size is 600. I divide this number by 600, and my average shoe size of men's shoes is 43.115 points. Yeah, and exactly as we expected. Yeah. Average men's shoe size is higher than average woman's shoe size, yeah, because it's the nature, of course. All right, come on, let's compute mean absolute deviation of women's and men's shoe size. We are going to use these formulas. The first formula is especially dedicated to the women's shoe size because, as you can see here, the data about the women's shoe size is presented by the relative frequencies. Yeah, so we have to adjust our formula into the relative frequencies categories. Here we will use this formula in the computations of mean absolute deviation of men's shoe size. Yeah, because here we operate by the frequencies, so in our formula there exist some frequencies. Let's start with the woman's shoe size. As you can see, in the first step, we are trying to compute the module of the differences, the module of the deviations between the middle of the classes and the arithmetic mean average woman's shoe size. Yeah? So in the first row, we will subtract 37 minus, here we have an appropriate category, the middle of the class minus x mean for women. Yeah? 37 minus 39.412. Yeah, and we compute the module of this kind of difference, and it's equal to 2.412. Of course, it's not necessary to have a cheat sheet. And here we have what? 40 minus 39.412, and this difference is equal to 0.588. Yeah, of course, and the next values are 3.588 and 6.588. Okay, but it's not the end. It's not the end. I need free space for another column. Wait a second, please. Yeah, I need the space for the next column in which the modules of the deviations will be multiplied by what? By the relative frequencies. Of course, relative frequencies from appropriate group of shoes, women's shoes. Yeah, so in this row I will compute the product between the modules of deviations and relative frequencies. So in the first row I have 2.412 by 0.426. Yeah? And the result is 1.028. In the next row I multiply the next module 0.588 by 0.395, and the result is 0.232, and then I have 0.459, and finally 0.336. All right. So I need the sum of the values from that column yeah, the sum is equal to 2.055, yeah, and actually this is the final result, 2.055 points, yeah. This is the average deviation of the woman's shoe size from the mean. Yeah, please write it down. This is the average deviation of the woman's shoe size from the mean. Yeah, here we have average level of considered phenomenon, average shoe size for women's shoes, 39.4 approximately, and this value and the values of our variable deviate from the average, from the mean, on average about 2 points. Yes, 2 points, 2 European points in the dimension of the shoe size. Alright, so now I will try to compute mean absolute deviation of men's shoe size. Here I need the difference, the module of the difference between the middle of the classes and average men's shoe size. So here we have 37 minus 43.115, and the result is 6.115. Of course, it's a module of this difference. Yeah, 37 minus 33.115, and then I have 40 minus 43.115, and the module of this difference is 3.115, 0.115, and finally 2.885. Yeah, and in the next column, because now I have only this element, I have to expand my analysis into the on the product. Yeah, product between the modules and the frequencies. Yeah, so here I have xi with a circle, which is represented by the middle of the classes, minus x mean for men's shoes multiplied by NIM. Yeah, so it means that in the first row I will multiply 6.115 by first NI and 1, which is 55. Yeah, and the final result is 336.325. In the next row I have 3.115 by 70. The result is 218.05. And then I have 31.28 and 585.655. Yes, and the sum of this column, is equal to 1171.31. Yeah, this is my partial result. This is the sum of the product between the modules and the frequencies. Okay, so I can write it down. The sum is 1171.31 171.31 divided by the population size. Population size is 600. 600. Yeah? 171.31 divided by 600 is approximately 1.952, yeah, points as well. All right, so it's very similar, yeah, very similar in absolute terms, of course. So here we see that we have the same problem. The average deviation of men's shoe size from the mean is about 2 points. Very similar to the previous one in the absolute terms, but as you can see here, we have one variable, okay, but we have two different levels of considered variable in population 1 and population 2, in population of women's shoes and in population of men's shoes. We have to solve this problem, so we need to compute the relative measure, of course, based on the mean absolute deviation. As you can guess, I will compute in both cases coefficient of mean deviation. All right, maybe like that. For women and for men, upper subscript. All right, for women, so here we divide mean absolute deviation for women's shoes by average women's shoe size. 2.055 divided by 39.412. 2.055 divided by 39.412. It's about 0.052. Yeah, so it's a low variability of women's shoe size. Yeah, we are talking about the low variability of the woman's shoe size. Okay, in the next case, men's shoes, we have the following ratio: dx with m upper index divided by x mean, of course, with m subscript. So here this is the ratio between average absolute deviation, yeah, of men's shoe size divided by average men's shoe size. In our case, it's 1.952 divided by 43.115, yeah, 1.952 divided by 43.115, and the result is very similar to the previous one, 0.045. Yeah, and it's time for the main conclusion. The question was Which population, men's shoes or women's shoes, are more varied in respect of shoe size? The answer is women's shoes are a little bit more differentiated in respect of the shoe size. A little bit more. Yes, because here we have the similar variability of the variable values in both populations, women's shoes and men's shoes. Fortunately, this is the last task connected with the topic classical measures of dispersion. Task 6 is very interesting and unusual task in which we have some partial results. But first of all, in one population that counts 70 statistical units, so we know that the population size is equal to 70. 70 statistical units have been examined, and the partial results have been computed as follows. Here we have the sum of the variable x values, the sum of the variable y values, the sum of squared variable x values, the sum of squared variable y values. Variable x is a weekly mineral water consumption in liters, and variable y is a weekly meat consumption in kilograms. So we have one population that counts 70 statistical units, and this population is characterized by two variables: weekly mineral water consumption and weekly meat consumption. Yeah? And we have to determine whether this population is more diverse. Is more diverse due to the variable x or the variable y values. Yeah? Okay, we have 70 people, yeah? And we are trying to answer the question in respect of which attribute, in respect of which variable, these people are more similar to each other or more diverse from each other, yeah? In respect of weekly mineral water consumption or weekly meat consumption, yeah? Alright. Oh my god. What should I do with this kind of data? Okay, I have n and I know the sum of x values and the sum of y values. So I am able to compute the average weekly mineral water consumption and the average weekly meat consumption. It's not a problem, yeah? I have all the data that are needed to compute means. Let's start. X mean is the sum from I equal 1 up to 70 of xi divided by n. Yeah, so in our example is 630 by 70 by 70. And of course you know that this kind of fraction is equal to 9 liters. Alright, of course we can also compute the average meat consumption, weekly meat consumption in this population. I need to divide the sum of every meat consumption of every statistical unit by n. Yeah, we sum up all the values of weekly meat consumption by 70 statistical units and divide this sum by n, and the final result is 1225 divided by 70. Okay, now I will use the calculator. 122.5 divided by 70 is 1.75 kilograms. Yeah, 1.75 kilograms. Okay. And what next? What next? Here we have the sum of squared values. Oh, I remember the fact that one of the formula contains this kind of element. Yeah, the variance, of course, the alternative formula for variance. Yeah, this is the sum from I equal 1 up to 70 of xi squared divided by n minus arithmetic mean of x squared. Yeah, so it's very easy to compute variance of x, and it's very easy to compute the variance of y, the variance of weekly meat consumption. The sum from y of y squared by n, so this is the average square of a weekly meat consumption minus squared average weekly meat consumption. Yeah. Alright, so in our example I have what? Okay, I need some more space. Let's start with the variance of x. Here we have the partial result. The sum of squares of weekly mineral water consumption is 6,254.5 divided by 70 minus 9 squared, of course. And the final result is 6,254.5 divided by 70 minus 81, of course, it's 8.35 liters squared. Yeah, liters squared. Okay, now I am able to compute the variance of weekly meat consumption values. The partial result is the sum of squares of weekly meat consumption 354.5 divided by 70 minus 1.75 squared. Alright, 354.5 divided by 70 minus 1.75 squared is about 2.002 kilograms squared. Yeah, kilograms squared. It's legible now. All right. Okay, but variance has no interpretation. I should compute here the standard deviation of the variable x and the values, and standard deviation of variable y values. The standard deviation of variable x values, it's the root of variance of variable x values. In our example, it's a root of 8.35. 8.35. The root is approximately 2.88 2.89 actually liters. Yeah, so it means that weekly mineral water consumption deviate from the mean on average around 2.9 liters. Yeah, this is the weekly mineral water consumption, and we know that the average deviation around the mean is plus minus 2.9 liters. And here we have the standard deviation of weekly meat consumption. It's a root of 2.002, a little bit above 2.002, the root, and of course it's something around 1.415 kilograms. Yeah, so we see that weekly meat consumption deviate from the mean by about, on average, 1.4 kilograms. Sorry, small correction. I've just checked in the dictionary that liters are spelled as follows. Yeah. And here. Sorry for that. Okay, let's come back to the example. I will give you some life facts. As you know, life is impossible without water. Yeah, it's hard to survive without water. Many people drink a lot of water. And actually, there are no ethical contraindications for this. Yeah, everyone needs it. We should drink at least 1.5 liters of water per day. Everyone needs it, so it's an objective criterion. But if we are talking about the meat consumption, yeah, the opinions are divided. Some people don't eat meat, yeah, for example, from ethical reasons, yeah. But we have also a group of people who loves eat meat, yeah, and they eat a lot of meat. For example, they love burgers, yeah, beef burgers, and McDonald's, KFC, and things like that. So we expect, in the statistical terms, yeah, that this population and we actually are more differentiated in respect of weekly meat consumption. Yeah, let's check it out. In order to check it out, we should compute the relative measure of dispersion. Here we have mean, average value, here we have standard deviation, so it determines that we are going to use coefficient of variation. Coefficient of variation for the weekly mineral water consumption, it's the standard deviation of weekly mineral water consumption divided by average mineral water consumption. In our example, it's 2.89 liters divided by mean value 9. Yeah? Take your calculators please. 2.89 divided by 9. It's about 0.321. Yeah. So as you can see, average deviation of weekly mineral water consumption represents about 32% of its mean. Okay, and let's compute the category connected with the weekly meat consumption. So we divide the standard deviation of weekly meat consumption by average weekly meat consumption. In our example, we divide 1.415 by 1.75. Yeah, 1.415 divided by 175, and the result is 0.809. Dear students, what does it mean? It is what we expected here. Yeah. So the main conclusion: this population and we actually are more differentiated in respect of weekly meat consumption. Yeah, we are more similar to each other if we are talking about weekly mineral water consumption. We are more different from each other when we talk about the weekly mineral water consumption. Thank you.